Welcome. Our invited speaker for today is Dr. Dan Rybarczyk from University of Wisconsin-Madison. I'll read a quick biography. He is an NSF astronomy astrophysics postdoctoral fellow at the University of Wisconsin-Madison. He used his observation with radio telescope to characterize the structure, chemistry, and evolution of gas in the Milky Way's interstellar medium. His earlier work focused on characterizing the structure of the galactic interstellar medium at larger, small scales. More recently, his primary interest has been understanding how the onset of molecule formation, the first step in the star formation process, begins. Beyond research, Dan is passionate about public outreach and engagement, especially using the planetarium as an educational tool. Dan,
Hi everybody, thank you for having me. I know this is off your normal Colloquium schedule, so I appreciate all of you coming. It's been great getting to meet some of you, and for those of you I haven't met, I'll just give a brief introduction. So I'm originally from Buffalo, New York. I did my undergraduate work at Boston University, and I lived in Boston for 4 years there. And then in 2018, I moved to the University of Wisconsin-Madison for graduate school. In 2023, I continued at UW-Madison as a postdoctoral fellow, supported by the NSF AAPF program. And I've been in Madison now, so over 7 years. And I'm going to tell you all about the research I do there, but I just want to mention besides the research, I do lots of outreach, including, as you heard, running a planetarium field trip program at UW-Madison. Okay, but in my research, I think about galaxies, and I focus mostly on our own Milky Way. And one of the key questions we ask when studying galaxies like the Milky Way is, what are galaxies made of? So knowing this is really important for understanding their structure and evolution. Okay, so of course, the Milky Way, our own galaxy, is home to stars, over 100 billion of them. And we can see a lot of these stars with our eyes or with telescopes looking at visible light. But there's also a lot more in the Milky Way that we can't see with our eyes, but we can detect with other instruments. And much of this is the stuff that exists between stars, the gas and dust between stars that we refer to as the interstellar medium, or ISM. So I'm saying ISM a lot through this talk. It means the interstellar medium. And the astronomer Bruce Drain defined the interstellar medium as the most beautiful component of galaxies. So this is responsible for a lot of pretty pictures. But more specifically, it is the gas and dust that exist in between stars and galaxies. Okay, but the ISM is not one homogeneous thing. It's multi-phase, which means that the gas in the ISM can exist in a wide range of temperature and density conditions, okay, with some extremely hot diffuse gas in some parts of the galaxy and extremely cold and dense gas in others. And in order to study all of this gas in the ISM, we need different kinds of observations. So for example, here you can see images of the Milky Way taken with radio, infrared, visible, X-ray, and gamma-ray telescopes. So we need many different kinds of complementary observations to understand ISM. And specifically thinking about what the ISM is made of, like most of the matter in the universe, most of the matter in the ISM is in the form of hydrogen. Okay, and we mainly find this hydrogen in one of two states. Okay, so we see atomic gas, which is just hydrogen atoms out in space. And we astronomers call this H1, that's a Roman numeral 1. So atomic hydrogen we call H1. Or in the coldest and densest parts of the ISM, which is where stars are eventually born, we can find hydrogen in its molecular form. So it's cold and dense enough for hydrogen atoms to bind together, forming molecular hydrogen, or H2. And these star-forming clouds that contain a lot of molecular hydrogen are referred to as molecular clouds. And then understanding how hydrogen gets converted from the atomic form to molecular clouds is critical for understanding the formation of stars and the evolution of galaxies. So in general, here is how the evolution of the multi-phase ISM does drive star formation and galaxy evolution. So diffuse atomic hydrogen gas that fills much of the galaxy is converted into cold, dense H1 clouds. These eventually become sufficiently cold and dense for molecular hydrogen to start forming, in which case when you're getting molecular clouds. In the densest parts of molecular clouds, star and planet formation takes place. And eventually, when stars die, they provide energy, as well as the heavy elements that they forged in their cores through fusion, back into the ISM, providing feedback and enriching the galaxy in heavier elements. Okay, so this is how galaxies evolve, with the ISM as mediator. Okay. My work largely focuses on the earliest stages of this process, so where diffuse H1 gets converted into molecular clouds. This is called the H1 to H2 transition. Okay, and it really marks the start of the star formation process. Unfortunately, studying this really important stage in galaxy evolution is not trivial. So for one, as I already alluded to, the atomic hydrogen itself is multi-phase. So H1 can either be in a warm, diffuse phase that fills much of the volume of the Milky Way, or in a cold, dense phase with more clumpy medium that precedes molecular cloud formation. But what we actually observe typically is all of the H1 together. That's what I'm showing on top here. In order to understand the H1 to H2 transition, though, we need to be able to disentangle the warm and cold phases of the hydrogen from our observations. Okay. And then as far as observing H2, it's actually extremely difficult. So H2 is extremely hard to detect directly because its symmetric structure actually prevents it from emitting strongly at the low temperatures where the H1 to H2 transition takes place. So if we want to study molecular gas in galaxies, we often need to use other tracers, which is a word we use to call other molecules that are associated with H2 that we can actually detect in these cold environments. And carbon monoxide, or CO, is the most common molecule in galaxies besides H2, and it's really easy to detect in cold environments. So that is our most common tracer of the molecular gas in galaxies, CO. Unfortunately, CO is actually not all that great at telling us the total amount of H2 in the ISM. And that's because the abundance of CO relative to H2 varies significantly across the ISM. And CO, crucially, only forms and survives in very dense environments, beyond what is required for the H1-H2 transition to get underway. So if CO is your tracer of H2, of the molecular hydrogen in galaxies, you're going to fail to account for molecular gas, especially in diffuse environments. Okay? And there's a significant amount of what we call CO dark gas. That's H2 without any associated CO emission. Okay, so here's an example from some chemical modeling of a spiral galaxy, where these are the spiral arms of that galaxy. The gray shows all of the molecular hydrogen that is formed, and the pink lines show us where there's enough CO to be detectable with our telescopes. Okay? And so here, all of this gray stuff, of which there's a lot that's not associated with pink, is what we call the CO dark gas. So some of my primary goals as an observational astronomer are to characterize the H1-H2 transition, which again marks the start of the star formation process, and this requires characterizing both the cold H1 and diffuse H2. Okay. And the primary tool I use to do this is radio spectroscopy. So I'm going to say a little bit more about this, but we essentially use radio telescopes around the world, some of which are shown here, to measure the distribution and kinematics, and when I say kinematics, I mean the velocity, how these clouds are moving through space, of atomic and molecular gas with spectroscopy. When I say spectroscopy, I mean looking at different colors of light, or for radio astronomy, we would say different frequencies. So each atom and molecule in interstellar space produces a characteristic spectrum of light, we often refer to as a chemical fingerprint. And that allows us to identify elements out in interstellar gas clouds. So if I see these lines here, I know that there is hydrogen in that cloud. Okay, but these lines can be shifted through the Doppler effect. Okay, so if a source is moving towards or away from us, and this is often due to the rotation of the galaxy, then these lines will be shifted to slightly longer or shorter wavelengths, or for our radio telescope, we would say slightly higher or lower frequencies. So what I observe is point a radio telescope at one part of the sky, and you observe light, rather than at a specific color, at a specific frequency. Okay, and so rather than being like a radio in your car, I like to think of it as each atom or molecule out in space broadcasting at a particular frequency. Okay, so rather than a radio station looking at different components of the ISM. Okay. And specifically, to study the atomic hydrogen, there's a line at 1420 megahertz. So we tune our telescope to 1420 megahertz, and we see emission from hydrogen atoms out in space. Okay. We can also tune our telescopes to the 90 to 100 gigahertz range. And at these frequencies, we see photons from CO, as well as other molecular tracers, which we'll see are really important. So specifically, let's look at what I do. So let's say that there's some interstellar gas cloud that you want to study. So I can look at this cloud and see light at those specific frequencies. Okay, but like I said, because of the Doppler shift, this light won't be just at one specific intrinsic frequency. It will be shifted because of the cloud's motion through space. So we usually measure the brightness as a function of frequency. Okay, so we have some range of frequencies over which we might see this cloud, okay, which results in a spectrum like this. So this is an emission spectrum. So in fact, we usually plot the velocity here, so we can actually compare different kinds of light. So we can look at light at different frequencies and see how fast the cloud is moving. And so often we'll see the brightness as a function of velocity in this talk. Okay, but now suppose that there's some background source behind the cloud, which is intrinsically bright over a wide range of frequencies. This could be, for example, a really bright radio galaxy, all right, and this produces what we call a continuum spectrum. Okay? Then when we actually see this source from our vantage point, looking through this cloud, we'll find that some of the continuum emission has been absorbed. Okay, so we take this spectrum and we end up with this spectrum. Okay, and this absorption occurs at exactly the same frequencies where we see the emission. So we can identify it as H1 or CO or whatever particular frequency we're looking at. And if there are multiple clouds along the line of sight, we'll see this behavior in multiple components. And they might be Doppler shifted if they're moving relative to each other, which is why we see two separate components here. And so these emission and absorption spectra are important for different reasons, but I'll just comment really quickly. So again, why we care about the velocities is that these velocities are largely shaped by the rotation of the galaxy. So understanding how things are moving through space can tell us something about where they are in the Milky Way. Okay, so thinking about the emission observations. These are great because they give us detailed information about the spatial distribution of gas. Okay, so we can point our telescope in any direction and see what atomic or molecular gas is present. However, as I mentioned, the H1 emission doesn't tell us about the phase of the H1. So is it the warm and diffuse H1 or the colder and denser H1? Both contribute to emission, and we can't automatically take emission observations and figure that out. However, the CO emission we can also measure across the entire sky. Okay, but remember that only traces some of the H2. So we don't learn about all of the molecular gas either through just emission observations. Meanwhile, the absorption observations are really important because they do let us identify the phase of the H1. So only the cold H1 is associated with strong absorption features like this. Okay, so in this spectrum, we have two spectra taken in the same direction, an absorption spectrum on top and emission on bottom. So here we're seeing evidence of the cold H1 absorption, that also contributes a little to emission. But the warm H1 contributes to the entire emission spectrum. Also, absorption spectra are more sensitive to diffuse gas, and so you can often easily detect an absorption clouds that are too faint to be seen in emission for CO or other molecular tracers or even H1. Okay, but we can only do these kinds of observations in directions where we have a background continuum source, like one of those radio galaxies. But there aren't a lot of these, and they're distributed randomly across the sky. Okay, so absorption only gives us limited information spatially. Okay, so the ISM is multi-phase. The H1 to H2 transition is a key stage in galaxy evolution, as it marks the start of the star formation process. But it's challenging to study because we need a variety of complementary observations which give us different information about the atomic and molecular gas. So my work is focused on identifying and characterizing cold H1 and diffuse H2 to understand the H1 to H2 transition. Specifically, I am concerned with understanding how we can reliably trace these phases of the ISM, with the end goal being to understand what conditions are necessary for this transition to occur, which sets the initial conditions for star formation. And I'm also working on developing tools to measure gas properties from our observations more reliably. Okay, so I'm going to start by telling you about the cold H1, which is best probed with 1420 megahertz absorption observations. So as part of a review paper on H1 in the Milky Way, I compiled all of the existing H1 absorption observations that met certain quality standards. Okay, and so here are some of the...
I have a question.
Yes.
So in the space, what light source you using for the absorption?
So the background source is usually going to be a quasar. So it's the synchrotron emission from electrons moving around a super hot black hole. And so this produces just a spectrum in the radio that's extremely bright over a wide range of frequencies.
But is there many quasar you need to aim in certain angle to get those?
Yeah, so there aren't a lot of them that are sufficiently bright to do this. So it all depends on your sensitivity. But there are something like a few dozen to maybe a few hundred for which we might be able to get good absorption spectra.
So that means the detection you have still need to aim in certain place.
Yes, exactly. So we only have very limited spatial information here. We're not mapping this. We're only getting it in certain specific directions. And so here's what those spectra actually look like. Okay, so here is an example of a direction where there's apparently no cold gas, right? So there's just noise here. Here's a spectrum with one faint component. Okay, so we see one cold gas cloud absorbing light along the line of sight. Here's one with a cold gas cloud along the line of sight that's absorbing very strongly. Here we see evidence of two gas clouds, one moving at this velocity and one at this. Here we see maybe three clouds, and we increase the number of clouds until we're seeing a line of sight with many, many cold gas clouds, all contributing to this absorption spectrum. Okay? And so I did a meta-analysis with these data. So the total sample I built was at least 5 times larger than any of the individual surveys. And among other things, we showed how the fraction of H1 in the cold phase along the line of sight depends on the total amount of H1 along the line of sight. Okay, and so here this is showing that increasing trend. Okay, we also showed how it varies with position in the galaxy. And this is really important for testing our understanding of the physics of ISM evolution. So models make specific predictions for these trends based on the assumed properties of the ISM. But until recently, it's been difficult to actually find observational constraints for these kinds of predictions. But another really interesting thing that we can do that's been exciting me lately with all of these H1 absorption observations is actually constrain the physical distribution of the cold H1 in the Milky Way. So our Milky Way is a spiral galaxy. It's shaped like a disk, okay, but the thickness of that disk is set by the balance of gravity and pressure. Okay, but the pressure contains the combined effects of thermal motions of the gas, turbulence, cosmic rays, magnetic fields, and more. Okay, and so by measuring the thickness of the cold H1 disk, we can not only say in what environments stars are more likely to form, but we can also provide key tests to see if our models of the galactic ISM, models containing all of that physics, are consistent with observations. Okay, so you can see here the vertical distribution of gas as a function of temperature and density from some such models. beyond just the thickness, we can also search for abnormalities in the shape of the disk that may be evidences of distortions that are caused by gravitational interactions of the Milky Way with other galaxies. So here in the bottom is an artist's impression of a warp in the Milky Way that we think was caused by such interactions. Okay? So if we see this in cold H1, we can say something about how these interactions play a role in driving the evolution of the multi-phase ISM and eventually star formation. Okay, so I and several other colleagues developed a tool to measure the thickness of the cold H1 disk from H1 absorption observations. So what we found was that for cold H1 near the sun, so we'll focus just on these points here right now, the value we got was actually a factor of 2 lower than what was previously reported. Okay, so the y-axis here shows the thickness of the disk, the x-axis shows the distance from the galactic center, so this is us. All right, so this orange point is the previously measured point, and this is our updated value, significantly lower than what was previously reported. The previous number, which is very heavily cited, came from a 1978 paper that actually contained a minor math error, which led to the overestimate. It's a very subtle problem, so it's hard for us to figure out what was going on. We also, though, found that the thickness depends on the H1 properties. So the spatial distribution of warmer and colder H1 is different. Okay, so the blue here shows you the thickness of the warm H1 disk, whereas the orange and pink show you the cold H1 disk. So they don't behave exactly the same. And this is important for understanding the evolution of the multi-phase ISM and saying where sites of star formation are set. So these results now, our updated values, suggest that the thickness of the H1 disk is similar in the inner galaxy as the solar neighborhood, which is actually consistent with recent high-resolution models of the galactic ISM. So this orange prediction shows, this orange line shows their prediction from some really sophisticated models of the ISM for the cold H1 disk, whereas blue is for the total H1 disk. You can see these are largely consistent with our updated measurements. The result that they produced when first reported seemed problematic, but now that we've actually confirmed their predictions with improved methods and data, they seem to be consistent. Okay. That was just the first step. So since we published that, a new catalog of H1 absorption measurements, more than 3 times larger than the meta-sample that I put together, was published using data from the Meerkat telescope, which is another radio telescope looking at 1420 megahertz. And this sample is now big enough to actually measure how the thickness varies across the galaxy. We have enough data to take a lot of subsets and figure out how this varies across the galaxy. So this is work being led by Wisconsin undergrad Osprey Schauer, and they've already found some very interesting results. So for example, if we look from the inner galaxy to the outer galaxy, we find variations in the thickness that could be evidence of warping and or flaring in the disk. Okay, so this kind of stuff has been studied with H1 emission before, but never with absorption. And it's important for telling us how those kinds of gravitational interactions might influence different phases of the ISM and star formation. We've also, very interestingly, identified some outlier clouds that are not following galactic rotation. Okay, so these could be clouds. So our model identifies the outliers, and these outliers could be clouds that have been ejected from the galaxy by supernovae explosions, or they could be material falling into the galaxy, which delivers fuel for the Milky Way star formation. Okay, so understanding how those clouds that aren't following galactic rotation fit into the galactic ecosystem is of great general interest because, for example, infalling and outflowing gas are important for regulating star formation in galaxies over cosmic time. So it's really important to characterize these structures. And the Meerkat data is really just paving the way for new facilities that are going to be online soon. So in the next 10 years or so, the Square Kilometer Array Observatory, or SKAO, is going to start collecting over 700 petabytes of data per year. Okay, so we're really starting to enter the big data era, even in radio astronomy. Okay, and then the next generation VLA, or NGVLA, is another array of telescopes that's hopefully going to be coming online soon, and also delivering huge amounts of data. So from both facilities, we'll get tons of new H1 absorption line observations, dwarfing what we currently have by several orders of magnitude. Okay, so with the tools and methods that we're developing now, we will be ready, once these facilities come online, to create really unbelievably detailed maps of the Milky Way's multi-phase ISM in the next 10 or 15 years. So what we're doing now is really exciting given what's coming in terms of the H1 absorption observations. Okay, so that's some of the work I worked on with the cold H1. But for the H1-H2 transition, we need to study the diffuse molecular gas as well. And a lot of my recent work has been fueled by two serendipitous discoveries of CO dark gas tracers. So these are signatures from the OH molecule in emission, which I'm showing here, and the HCO plus molecule in absorption, which I'll show momentarily. So these are just two molecules that exist in the ISM. But unlike CO, they happen to be associated with really diffuse molecular gas, close to the H1-H2 transition. Okay, so here's an example, of the OH emission from Michael Bush's work. So we're looking in a particular direction of the sky, and we have a spectrum of different tracers in that direction. So the blue shows you the H1, the atomic gas, and we've labeled here that some of these features are associated with spiral arms of our galaxy. The CO, so tracing the molecular gas, is isolated to just one component. Okay? But if we look at OH, which is a molecule that we think is associated with diffuse H2, we see emission from that molecule, so both the green and red lines are both tracing OH, across basically all of the regions where we see H1 emission. Okay, so OH is tracing diffuse molecular gas. So this is telling us that there's diffuse H2 everywhere, essentially along this line of sight, where we also have atomic gas. Okay, and you would never know that by just looking at the CO. Okay, so Michael Bush, the discoverer of this OH component, and I have been working together on comparing these two new signatures and delivering some of the best ever constraints on CO dark gas properties. All right, so here I'll show you some of the results from my work. So these are, again, absorption line observations in one direction. The black shows us where the cold atomic gas is. Remember, each of these components shows us the cloud in the galaxy, and where it's positioned on the x-axis is just based on its velocity, so how it's moving through the galaxy. And the pink is showing us the, HCO plus absorption. So HCO plus is just another molecule in interstellar space. And we see absorption from two components here. And if we look at the CO emission, we actually find that this gas is not CO dark. It's what we call CO bright. There's CO there, and it seems to be tracing the same two components. Okay. But if we zoom in on the HCO plus, we find that there's actually a significant amount of HCO plus virtually everywhere where we see cold H1. Okay, so zoom in on this spectrum here, and we find this low-lying but still significant signature in the HCO plus absorption. Okay? And if we look at the CO, which I'm showing here in absorption, even more sensitive than the emission, we would never know that this diffuse gas is there. And I have actually a nice way of looking at these data, so I'll pass this around. So this is a 3D print of the spectra. So the one closest to you, if you look at it this way, is the CO, and you'll see that it's narrowly restricted in velocity. The HCO plus, though, is very broadly distributed, and you'll see the same thing in the H1 absorption, which shows the cold H1. And then the H1 emission you'll see is even broader. So you'll see emission where we don't see absorption. That's warm atomic gas. So feel free to pass that around. Okay, and here's some preliminary complementary work showing that the OH emission, which Michael, my friend, originally detected, is indeed tracing the same thing as the HCO plus absorption. So we have a compelling case that these are both tracing diffuse molecular gas, and that they're largely consistent with each other. And so now we can look at the properties of clouds that are associated with diffuse CO dark molecular gas. And we find systematic differences compared to the gas that is traced by CO. So among other things, these diffuse molecular gas features exist in more diffuse environments, and in those environments, there's a lower fraction of hydrogen in the form of H2. So less of the hydrogen has been converted from the atomic to the molecular gas. This is strongly indicative that this is tracing gas very near the H1-H2 transition. Okay, so these observations open a brand new window into diffuse gas that is partially molecular, but is not so dense as the CO bright gas in these regions. So we have ongoing collaborations with people trying to explore in greater detail this diffuse CO dark gas with HCO plus and OH. And this realization is actually really powerful. Okay, so it turns out that we already have a lot of really useful archival HCO plus observations, some of which were observed for entirely other reasons, that we can now use to investigate molecule formation in diffuse environments. And so, for example, I worked with former Wisconsin undergrad, Lucy Steffes, who's now a graduate student at Arizona, to use archival observations to measure HCO plus absorption towards this thing that we call, the Magellanic Bridge, which is a long stream of gas connecting the Milky Way and its two nearest satellites, the large and small Magellanic Clouds. Okay, so this is really interesting because the conditions in the bridge are very different than those in the Milky Way. And we actually think that they reflect what gas would have been like in galaxies in the early universe. Okay, so we can learn about the history of molecule formation and star formation by using the stream now as a laboratory. Okay, so we unfortunately only measured upper limits, but these are still useful for understanding how star formation might or might not occur in environments very different than the Milky Way. Another really cool and exciting application of this is that the submillimeter array, or SMA, which is a radio telescope in Hawaii, actually observes bright continuum sources, so the exact kind of thing we need to measure HCO plus absorption, every day as part of instrument calibration. And these calibration observations are actually sufficient for our science. Okay, so I worked with a former SMA postdoc, and we have a pipeline now that makes it easy to extract scientifically useful observations from SMA. So here's a clear absorption line detection, that's actually CO, from our proof of concept tests. And so this offers a really amazing opportunity. So we already have tons of data. So students can use these archival observations to make perhaps the most sensitive absorption spectra we have ever at these frequencies. Okay, and so we can get really sensitive observations that would give us an unprecedented view of the physics and even chemistry of gas near the H1 to H2 transition. Already existing data. Okay. And finally, I just want to touch on, I've been talking a lot about emission and absorption observations and what they teach us, but I haven't really told you precisely how we extract useful information from these observations to study ISM physics. So let me talk a little bit now about how we do that and some new tools improving our ability to do that. Okay, so as a general background, we know at what color, or in radio, at what frequency a line is produced just from quantum mechanics, right? The structure of the atom tells us where the line should be produced. So for example, the H1 line is at 1420 megahertz. And here, as usual, I'm showing this example in velocity rather than frequency. This is the convention. Okay. But the ISM isn't just static gas, it's moving. And how it moves is imprinted on our spectra. Okay, so I already talked about how lines can be shifted by the Doppler effect, okay, if the cloud is moving towards or away from us. But the line can also be Doppler broadened by the internal motions of a particular cloud. Okay, so for example, the thermal motions mean that some atoms and molecules are moving towards or away from us. Okay, and that causes this line to spread out a little bit rather than being at one particular frequency. And if the temperature is lower, those thermal motions will be slower, and the magnitude of that Doppler broadening will be smaller. Lines can also be broadened by turbulence. Right? So this is the kind of eddy-like motions of fluid. Okay, and this in galaxies can be driven by supernovae or spiral arms passing through the ISM. Okay, and these eddies too will broaden our spectral line as some of the eddies are driving gas towards or away from us as the gas gets stirred up. Okay, so turbulence is important in lots of astrophysical processes. It tells us about the galactic scale processes that drive turbulence, but it's also important for compressing gas, which in my work can be important for getting to the conditions where we have sufficiently cold and dense gas to form molecules. But what we actually observe with our telescopes is just the spectrum, okay, which includes the combined effects of turbulence and thermal motions. Okay, but if we want to understand the physical properties of the interstellar medium, we need special tools to disentangle these. Okay, and one thing that I haven't even mentioned is that amplitude is also significant. Okay, so I'm going to ignore that for this, but we can learn about the density and size of the cloud based on the amplitude of the line. Okay, so what my collaborators and I have worked on is to build a Bayesian model, okay, so where we use our prior knowledge of the ISM physics to determine these physically meaningful quantities from spectral line observations. So specifically, we build a model in terms of physically meaningful quantities, okay, and ask for what plausible range of these quantities in the ISM could we explain our observations. And in the end, we don't get a single number, but a distribution of possible values, which allows us to meaningfully quantify our uncertainties. Okay, and so this complicated plot here shows for each pair of physical quantities, which is each of these rows and columns, what is the range of values that could explain our observations? And you can see that there's, rather than a single point, a cloud of possible points. And some of these quantities are also correlated in interesting ways. Okay? And so we can actually capture all of that correlation and uncertainty by using this kind of model. All right? And so this can be applied to emission or absorption observations, or both, which actually gives you the best constraints. And preliminary tests on a Bayesian spectral line model for H1, which was led by Professor Trey Wenger, who's at Chico State. On some simulated data where we actually know the answer, we know the density and temperature and turbulence, it performs significantly better than standard methods that are used in other ISM work. Okay, so with our current H1 model, we can identify clouds in spectra, and for each cloud measure the density, temperature, pressure, and turbulence, as well as robust estimates of the uncertainties on these quantities. So one application of this is to learn about cold gas without the need for absorption line observations. So for example, many other galaxies are so small on the sky that there are no bright background continuum sources behind them, so we can't measure H1 absorption in these galaxies. Okay, but now we can still estimate the temperature of the H1 just from emission. Not as accurately, but it's a step in the right direction, and it's really the best that we can do. So here's an example of that application. So this is work led by Fabian Caballero Vargas, who is a New Mexico Tech undergrad that I've been working at since he did an REU in Wisconsin. So this is data from an incredible new survey from the VLA, which is a radio telescope array in New Mexico, part of a project called the Local Group L-band Survey, or LGLBS, which so far has surveyed 6 galaxies in unprecedented detail. So in one of these galaxies, called WLM, Fabian and I are looking at the temperature of H1 as measured with this new Bayesian model. And you can see, for example, cold gas, this arc-like structure in the galaxy. This, we know from other observations, is actually associated with a giant shell that was blown into the interstellar medium by supernovae over the past tens of millions of years. Okay, and so this is now telling us about how stellar feedback can trigger the formation of cold H1 and eventually stars. One of the reasons this is exciting is because the galaxies in LGLBS are very different from the Milky Way. So again, like the Magellanic Stream, they provide great laboratories for testing our understanding of fundamental processes in the ISM and how they might be different in different kinds of galaxies. And these kinds of galaxies we expect are what galaxies look like in the early universe. So really powerful for understanding cosmology. But there's no reason to stop at H1. So we haven't yet incorporated our molecular ion tracers into the Bayesian framework, but it will be fairly straightforward to do so. The software infrastructure is already built, and so this is a great opportunity for researchers, including our undergrad colleagues, to come in and help us better understand what's going on with the H2 transition. So we have multiple line observations, and having these different lines actually dramatically improves our estimates of the properties of the gas. And again, these observations already exist. So just to wrap up, the H1-H2 transition is a really important stage in galaxy evolution. It's the first step in the star formation process. To study it, we need a variety of complementary observations, including 1420 megahertz absorption observations, observations of different molecular gas tracers, including tracers that aren't CO, and tools to extract physics from spectroscopic observations. So my work has used new and existing H1 absorption observations to characterize the properties and spatial structure of cold H1 in the Milky Way. I've also identified a significant reservoir of diffuse molecular gas that's invisible to CO. And recently, we're using new statistical tools developed with collaborators, including Trey Wenger, who led some of that work. We're characterizing the structure of cold H1 in galaxies beyond the Milky Way. So these have all improved our understanding of where and how the H1-H2 transition occurs. And this is important for understanding galactic evolution as well as testing models of the ISM. And it's really laying the groundwork for big data coming soon. So undergraduate colleagues have been involved in basically all phases of this research. And the future looks really bright for radio astronomy. So there's lots of opportunities for researchers at every level over the next couple of years. Okay, so in the next 1 or 2 years, we'll have a clearer picture of the cold H1 distribution from these meerkat observations. We'll get more observations of diffuse molecular gas tracers. We'll get a detailed map of the distribution of cold H1 in a different galaxy. In the next 5 years, we can extend this work to other galaxies in the same survey that Fabian and I have been working on. We'll also be able to extend our analytical tools to other ISM tracers and build a large and extremely sensitive catalog of absorption line observations. And then in the next 10 to 15 years, if all goes according to plan and the SKO and NGVLA come online as planned, we'll be prepared to carry out far more detailed analyses of the gas in the Milky Way and nearby galaxies that just aren't possible with current facilities. So it's a really exciting time for scientists at every level. And sorry, I left a lot of time, but I'm happy to take any questions in the next couple of minutes.
Maybe I should have, maybe it got past me, but which was the local group galaxy that you and Fabian were looking
Yes,
at?
this is WLN.
Okay.
So it's one of 6 local group galaxies in the LGLBS. We also are looking at M31 and M33, but the rest are isolated dwarfs.
Questions?
Is there any way to, it's obvious you can tell which direction stuff is. Is there any way to tell how far it is?
That's a great question. If I go back to, the answer is kind of. So we know, in some sense, how the Milky Way is rotating. And so we can obtain what we call a kinematic distance. So based on some rotation curve of the Milky Way, how we think the galaxy is rotating, we could say, at what distance would we expect a gas cloud to be producing this signature at this velocity? Those are unfortunately not very reliable though. So if you try to make a map of the Milky Way using kinematic distances, we find independent measurements where we can actually measure the distances of things are quite unreliable. And so we have some constraints on how far away things are, but it's really difficult. Now one really cool thing is that in the last 5 or so years, we've used observations of dust to actually build a 3D map of the Milky Way out to about 1.25 kiloparsecs, so that's about 4,000 light years. And so it's really like kind of just our area of the galaxy. But we have the first 3D maps of the ISM in the solar neighborhood, which is incredible. From those, we can compare to the spectral line observations and get very good estimates of the distances, but that's very challenging. There are people who are trying to work on a full 6D map, so the 3D positions and 3D velocities of gas local, so nearby to the sun, where we can actually carry this out. But it's very, very challenging. And in general, most of the things I'm looking at, we don't really have a good constraint on exactly where they are in the galaxy. That's one thing we want to figure out.
So from these H1 to H2 transition, so where is hotter? Outside of a galaxy is hotter or center of galaxy is hotter?
Yeah, so the temperature throughout the galaxy varies. So the temperature of gas in interstellar space is very high, so most of that gas is just ionized. However, it's very low density. Inside of galaxies, there's a mix of cold and warm gas, and so if we look back at...
Averaging.
Sorry?
Averaging.
Yeah, so here you can see that there's this gas down here traces very hot gas, this traces very cold gas. So in spiral arms, there's a lot of cold gas, that's where stars mostly form. However, those stars release a lot of energy and end up heating the gas. And so there's a mix of hot and cold gas everywhere. So the cold molecular clouds eventually are destroyed by the stars that they form. And so it's really a constant evolution. There's not one place in the galaxy that's particularly hot or cold. The places where the galaxy is coldest is where the molecular clouds form, but then they birth stars, which then provide stellar feedback and heat things back up. And so there's just a mix of hot and cold gas throughout the galaxy.
Oh, me, okay. So the dwarf galaxies, the streams that went from the Milky Way to the dwarf galaxies, so how do those form, and why do you think because you mentioned they're different and some
Yes.
is more primordial.
Yes.
So why is that?
So those form from essentially the Magellanic Clouds kind of falling onto the Milky Way. So they're gravitationally attracted to the Milky Way, and so they've passed through, and actually as they pass through, material was stripped off of them. And so that's what produced the stream. So the stream is the result of these things passing through and having material stripped as they move away from the Milky Way. But the reason that they're more primordial is so the Magellanic Clouds are at lower metallicity, which means that less of the heavy elements that are formed inside stars have been ejected into their interstellar medium. And so early in the universe, right, there was just hydrogen and helium. Gradually, through star formation and star death, the interstellar medium has been enriched with these heavier elements. So in the Milky Way, that's happened to a much greater degree than it has in the Magellanic Clouds. And so they are similar, and the gas in the stream is similar to the Milky Way early in the universe. The Milky Way has since been enriched by all the star formation that's happened here. But earlier in the universe, it would have had fewer of these heavy elements like carbon and nitrogen and oxygen. And so we think, and so those elements are important in the star formation process as well. And so we think that that gas is what the Milky Way or other galaxies would have looked like in the early universe. Yes?
So you said the convention was to express those graphs with by velocity relative to us. What direction is that velocity?
So that's a great question. So it's the velocity we typically plot for studies of the Milky Way is defined with respect to the local standard of reference, or the LSR, we call it. And so those are what we call LSR velocities. So it's basically if you take the sun's motion through the galaxy, remove that, it's like how fast are these clouds moving with respect to the sun in the Milky Way. So we treat basically our motion through the galaxy as the standard of rest. So clouds that are near zero are essentially moving with us through the galaxy, and these are mostly nearby clouds. Clouds at higher velocities, and I can actually show Michael's plot again. Sorry. Yeah, so zero here, velocity kind of represents stuff that's nearby to the sun. So this is stuff that's moving with the sun through the galaxy. But at these higher velocities, these are parts of the galaxy where gas is rotating at wildly different velocities. And so this looks into the outer galaxy. Here we're looking at the inner galaxy. And so it's determined by the galactic rotation.
Okay, because the redshift would only be relative to how it's moving away from us, right?
Right, yes, exactly. So this is how it's moving projected just along the line of sight. So this is a radial velocity. And so we have only the one-dimensional component of the velocity, but we can use the equations of galactic rotation to convert that given which direction we're looking in. And so based on the galaxy's rotation and where we're looking with respect to the galactic center, tells us basically how fast the gas should be moving. And so that's how we can infer some kind of distance from a velocity.
And I'm sorry, I got to follow up on
Sure.
that. The Magellanic Clouds.
Yes.
So if they have low metallicity, do they have a high proportion of small stars that are long-lived because they haven't blown up a bunch of
Not necessarily, they just have a lower star formation rate. And so they form stars less readily than the Milky Way, and so that's part of why they have lower metallicity.
Okay, there is a class after us, so let's send our speakers.